Now we are going to talk about another clinical application for stacked ABR. Stacked ABR can be used to help identify patients with Meniere's disease. You probably now have already known that stacked ABR is a technology based on derived band ABRs. It is also supposedly to be helpful in identifying patients with Meniere's disease. Before we can get to details and how it works, we need to understand a phenomenon which is called under-masking phenomenon. It's basically a reduced effectiveness of high-pass noise on the ABR latency in response to click stimuli. CHAMP is marketed by Biologic. CHAMP stands for cochlear eye drops amplitude measurement procedure here. CHAMP is basically a commercial package utilizing stacked ABRs and use that to help identify Meniere's disease, and is commercially available in Biologic. And again, before we get into details on how to use it, we need to understand a phenomenon called under-masking phenomenon, and we'll get to details in the following slides. This slide is a drawing that I make trying to explain the under-masking phenomenon. So on the top, we shows the basal membrane of inside the cochlea in response to clicks, acoustic clicks. As you know, clicks are broadband stimuli, so it will excite all areas along the cochlea, and we will get, say, a click-evoked ABR looks like this, and let's say Wi-Fi latency is here. Now we are going to present clicks together with high-pass masking noise to the test ear. So because we deliver a high-pass masking noise, the basal portion of the cochlea is masked out by the noise, and so only the area, the cochlear area that is more toward the apical end, can respond to the stimuli, because the apical, the basal region of the cochlea is masked out by the high-pass masking noise. So as the cochlea, as the area in the cochlea that is responsible for the response is moving more toward the apical end, we are expecting responses with longer latencies, because the basal membranes toward the apical end is wider and floppier. So for the evoked ABR here, we would expect the Wi-Fi to be prolonged. I mean, basically all waves will be prolonged, but we focus on Wi-Fi for now. So let me review the two conditions. When we have clicks only, and we have Wi-Fi latency here. When we have clicks plus high-pass noise, because high-pass noise masks out basal regions of the cochlea, so the area in the cochlea that is responding is moving toward the apical end. As a result, we will have a longer latency for ABR Wi-Fi like this. So initially it was here, follow my laser pointer. Initially Wi-Fi latency was here. Now it gets prolonged to here. So from here to here. So it is as expected, because this is the normal physiological properties for the cochlea and human auditory system. This is the effect of delivering masking noise to the test ear. So this is called masking effect. When we present ipsilateral high-pass masking noise, we expect ABR Wi-Fi latency to be prolonged. And for a normal cochlea, this prolongation, this increment of Wi-Fi latency is quite substantial, like shown here. However, in patients with Meniere's disease, when we deliver when we are conducting the second condition, because there is a big high drop in Meniere's disease patient, the pressure is high. There's a high pressure within the endolymph, and as a result, the basal membrane becomes tense. You know, it's when the pressure for endolymph is under high pressure, then the basal membrane got tense. It cannot move as freely as it was. So when the basal membrane got tense, it was not floppy anymore. Now it becomes tense because of the high pressure produced by the big eye drops. As a result, the latency may still prolong, but not prolong as much as it should be for normal patients. So the ABR waveform evoked in patients with Meniere's disease is plotted in light green here. I don't know the color what color you wanna save it. Let's say yellowish color, yellowish green, greenish yellow. So this say yellowish green waveform is the ABR wave you would obtain in patients with Meniere's disease. In this case, the prolongation of ABR wave 5 will not be as much as it should be when compared to normal patients. In normal patients, we expect to see quite substantial prolongation in ABR wave 5. However, in patients with Meniere's disease, because of the big eye drop, high pressure, basal membrane got tense, the latency prolongation is not as much. So this is called the under-masking effect, because we expect this amount of masking effect in normal patients. However, in patients with Meniere's disease, such masking effect goes under our expectation. So it is called under-masking effect, because the masking effect goes under our expectation. I hope this makes sense. So the two lines at the bottom is more like a brief recap. For normal patient, when we deliver ipsilateral high-pass masking noise, the area in the cochlea that is responsible for the ABR waveform goes more toward the apical end. And in that area, the basal membrane is softer and floppier. As a result, latencies are prolonged. So this is called the masking effect. We marked in red. For under-masking effect, that is in patients with Meniere's disease, there are big eye drops in the ear and high pressure in endolymph. As a result, basal membrane becomes tense. As a result, the ABR latency is not prolonged as much as we would expect, and that is called under-masking effect. This is another figure that I draw to help explain under-masking phenomenon. So let's look at the basal membrane in a normal cochlea. The basal membrane at the base is narrow, stiff, and rigid, whereas the basal membrane at the apical end is wide, soft, and floppy. And this is the fundamental reason that Wi-Fi latency got increased when we deliver ipsilateral masking noise. In patients with Meniere's disease, because the big eye drop here, the cartoon drawing here is not very good. My apologies. We have say cochlea here, and semicircular canal, and the sacula and ventricle, and then the endolymphatic sac. The endolymphatic sac say was small in the beginning, and then because of the Meniere's disease, fluid backup in the lymphatic sac. I exaggerated quite a bit in the drawing here. So just to illustrate the idea, the endolymphatic sac becomes really big. This is called the big eye drop, and the big eye drop indicates it's a high pressure system. So the basal membrane at the base, got stretched out. Basically the basal membrane got stretched out everywhere, including the apical area. Because the basal membrane at the apical area becomes tense, the latency is not prolonged as much as we would expect. So the masking effect goes under our expectation, and that's the reason we call it under masking phenomenon. CHAMP, cochlear hydrops amplitude measurement procedure. The CHAMP is based on the philosophy and procedures that is the same as the wrapped band ABR recordings. The theory and findings are that Meniere's disease do not show as much change in Wi-Fi latency as normal people will show when you change the high-pass cutoff frequency for the masking noise. In theory, endolymphatic hydrops change cochlear mechanics so that the ABR latency does not change as much as you decrease the cutoff frequency of the high-pass masking noise. So it's the same as you collect the wrapped band ABR recordings, but this time you compute change in latency and amplitude as you change the cutoff frequency for the masking noise. In normal people with no Meniere's disease, you expect to see latency prolongation that are longer than 0.3 milliseconds. In terms of the amplitude ratio, we would do the Wi-Fi latency produced by click with 500 Hz with high-pass noise cutoff frequency at 500 Hz compared to ABR Wi-Fi evoked by clicks alone. The amplitude ratio is going to be less than 0.75. So in other words, in normal people, we expect to see latency delays, and we expect to see the delay that is more than 0.3 milliseconds. We also expect to see amplitude ratio changes. The amplitude ratio would become less than 0.75 when we do these two comparisons. When we use the Wi-Fi amplitude evoked by clicked and high-pass masking noise cutoff frequency at 500 Hz compared to the Wi-Fi amplitude evoked by clicks alone. So again, these are the some basic ideas and explanations for CHAMP. CHAMP is a commercially available package that you can buy in biologic commercial ABR systems. So this figure is one I copied from a book. It's showing similar ideas. So, but it's here you can see we have ABR waveform obtained by using clicks alone, just clicks, and we have Wi-Fi here. Pretty good looking. And we also have ABR in response to clicks plus high-pass noise cutoff frequency at 8,000 Hz. We also have another ABR waveform evoked by clicks plus high-pass noise cutoff frequency at 4,000 Hz, and so on and so forth. We have high-pass noise cutoff frequency change from 8,000 Hz decreased down to 0.5 thousand Hz. So as you can see from the ABR waveforms, the latency of Wi-Fi increases as we decrease the cutoff frequency for the high-pass noise. So Wi-Fi latency was here, and it goes and it becomes prolonged when we decrease the cutoff frequency for the high-pass noise. The figure on the left shows the amplitude spectrum for the acoustic stimulus. The top panel shows the frequency spectrum for clicks. As you have already known, clicks are wide band frequency stimuli, so it contains a wide frequency band. And the panel on the bottom shows the amplitude spectra for those high-pass noise. Say if we set cutoff frequency at 8,000 Hz, then only the high frequency portion will pass. So only this portion of noise will pass. And now when we decrease the color frequency to 4000 Hz, then only this portion of high frequency components of noise will pass. 4000 Hz with this region to pass. When we further decrease the color frequency to 2000 Hz, then this portion of high frequency components of the noise will pass, and further decrease to 1000 Hz and then 0.5 thousand Hz. So these frequency spectra are the amplitude spectra for the high pass noise at different color frequencies. This slide shows another figure that I copied from the literature. On the left-hand side shows a series of derived band ABR recordings in patients with Meniere's disease. So on the top trace is the ABR waveform recorded evoked by using clicks only. So in clicks only, we mark the wave file here, and we draw a vertical line as a reference line. And then we have ABR waveforms recorded by using clicks plus high-pass noise at 8000 Hz and at different color frequencies. As you can see, now the 500 Hz color frequency for the high-pass noise is probably the one that we want to compare the most. So here, as you can see, the difference, the latency difference between the reference wave file latency, which is the unmasked ABR wave file latency, in other words, just clicks alone, compared to the wave file latency that we evoked by clicks and high-pass noise with color frequency at 0.5 thousand Hz. As you can see, the latency delay is just a little bit, not a whole lot. On the right-hand side shows similar ABR recordings. However, it's from patient with non-Meniere's disease. So same thing, we record ABRs by using clicks only. This is unmasked ABR. We have wave file peak marked here, and we draw a vertical reference line. And then we do the same thing. We record ABR waveforms in response to clicks plus a high-pass noise at different color frequencies. And again, at this point, we focus on the last condition because it is supposed to produce the longest latency delay. So this is the ABR waveform evoked by using clicks plus high-pass noise with color frequency at 0.5 thousand Hz. As you can see, the latency delay is a lot. I mean, this is normal. In normal cochlea, when the apical portion of the basal membrane is wide and soft and floppy, we expect to see a substantial latency delay. However, in Meniere's disease, because the high drops and the big pressure, the basal membrane becomes tense, especially in the apical area. Such a delay is now minimized. So again, this shows the undermasking phenomenon. This slide is a summary for stacked ABR and Meniere's disease and how to use it to help diagnose Meniere's disease. Both stacked ABR and CHAMP require very quiet subjects, and both are time-consuming due to the constraints that are inherent to derived band ABR recordings. The CHAMP is available in biologic software package. However, we will need more data to confirm sensitivity and specificity outcomes for using CHAMP to help diagnose Meniere's disease. So these are the summary and the information I want to go over in terms of stacked ABR and Meniere's disease.